Hi people, this is the second video covering the TSSM Physics Trial Exam of 2019. The first one covered the multiple choice questions. This is going to cover the written questions from questions 1 to 9 inclusive. So if you're looking for answers for 10 to 17, that's in the third video. This is questions 1 to 9. Okay, written section begins. Let's have a shot. Question 1. Okay, I'm assuming you have the questions with you, but I'll occasionally show them to you. Some I will, some I won't. Excuse me, this one has a diagram, so I think it's worth showing. Okay, figure 1 shows the electric field around two charges P and Q. What are the polarities of charges P and Q? Explain your answers. Okay. Electric field lines go away from a positive and towards a negative. So these, So these arrows that are going between the two of them, they're the only ones that really matter, are going away from Q and towards P. So that has to be positive. Excuse me. So that has to be positive and that has to be negative. All right. The fact that there are some arrows going towards this apparently positive charge just means there might be something over here that's even more positive. Don't get fooled by that. The arrows you need to talk about are the ones that are going between Q and P. All right, the ones that are starting from one and going to the other. So compared to each other, this is positive, this is negative. All right. And your explanation only just has to say that arrows move, the way that the electric field is drawn is by showing arrows moving away from a positive charge and towards a negative charge, or to show the direction that a unit positive charge would move. All right. That's fine. Excuse me. Explain why figure 1 could not represent the gravitational field around two masses. That's what B says. I know it's out of screen, but I want to keep the diagram here. Gravitational fields only attract. This is repelling. That's the simple answer. Gravitational fields don't repel, and this one is repelling. This is a field that's showing you that the force would be pushing something away from it, so it can't possibly be gravitational. Okay, question 2. I've got a slightly bigger drawing of this one so that we can play around with it a little bit. It says a charged particle R passes from left to right through a magnetic field of a magnitude of 0.025 Teslas, all shown in figure 2. The particle travels at a speed of 1.5 by 10 to the 5 meters per second, and the magnitude of the charge on R is 3.2 by 10 to the minus 19 coulombs. Okay. The path of R is curved out of the page as it passes through the magnetic field. In other words, it goes up towards you, towards the camera. So it's curved and going like that. Excuse me. Does R have a positive or negative charge? Okay, this is either a right-hand rule or a left-hand rule thing. One of them is going to work. That's positive, that's negative, right? Left is negative, right is positive. So I'm going to try the right hand first. And already, just holding my hand like this, I can see that this is the correct answer, right? Magnetic field lines are your fingers, your thumb is the direction of the charge, and your palm shows which way the force will go, and this is going to be forced up, right? And they told you that it was going to curve up. It always ends up going in a curved, it always goes in a curved path when it experiences this sideways force, because the force is always at right angles to the direction of its motion. All right, so right-hand rule. You don't have to explain that one at all. You just have to put positive or negative inside the box, so it's positive. It says the path of R, this is part B, the path of R has a radius of 12.5 centimeters. What is the mass of R? Now for this you have to realize two things. Firstly, because it's going in a circular path, the force on it is mv squared on R, right? That's the force, that's centripetal force. That's the formula for centripetal force. That's how to calculate the force of anything that weighs anything going around a circle that's that big at that speed, right? It doesn't matter what's causing the force. That's how to measure how much force is causing something to go around in a circle. This is going around in a circle, right? In this particular case, we know what's causing it because it's in a magnetic field. Excuse me. And this is the formula for the force that is on a charged particle in a magnetic field. So that is the cause of this result. Right? So you start with this, and you can cross a couple of things out here. There's a V, there's two V's there and one there, so you can get rid of that. So mv divided by r equals qv, and we're trying to find the mass of r, right? So we're solving this to find m. So if you rejig this, you end up getting qbr divided by v. There you go. Solve that for m, you get the job done. It comes to 6.7 by 10 to the minus 27 kilograms, but that's where the solution comes from. Part C is a bit of a left field one. It says, explain why some electromagnetic radiation is produced from the particle. Okay, there are two ways that electromagnetic radiation, or photons, right, light, is made, right? One of them is the old, inside an atom, right? When an electron jumps up from its ground state to a higher orbital for a while because it gains energy somehow, and then when it jumps back down, it releases that energy in the form of a photon. That's one of the two ways that light is made, electromagnetic radiation is made. The other way is if any charged particle, proton, alpha particle, electron, whatever, right, neutrino, if any charged particle accelerates. And accelerating is any change in its velocity. A change in direction is a change in velocity. So this is curving. Right? It's going around in a circle, so it is changing its velocity. So it can release photons as it does that. Right? Two ways to make light. One of them is this. The other one is to accelerate, speed up, slow down, or change the direction of a charged particle. Question 3, hang on a second, I'll get rid of it. Question 3, pardon me, a spherical asteroid has a mass of that, and the gravitational field at the surface of the asteroid is that. Calculate the radius of the asteroid. All right, a couple of things here. This here, F equals G m1 m2 divided by r squared, right? That's the formula for the mutual gravitational force between two objects that are both attracting each other, right? But every F can be calculated by F equals ma, right? Which means if you divide any F formula by one of the m's, you get the acceleration. So if you cross that out, what's left is the acceleration due to gravity of that mass, right? So little g is just gm on r squared. That's where that formula comes from, okay? So we're going to use that for this one. Question 3, it says, calculate the radius of the asteroid. They've given us everything else, right? We know its mass, we know g, it's on the data sheet. Excuse me. They gave us this. Now, one more thing you need to know about this question that's written in this question. They told you that the gravitational field at the surface of the asteroid is 0.25 newtons per kilogram, right? That is the same as meters per second squared. This is an acceleration. This is g, okay? Newtons per kilogram comes from this, right? A equals F divided by m, so the units of it would be newtons per kilogram, right? Force is in newtons, mass is in kilograms. That's where that comes from. So that is the same unit as meters per second squared. It's just derived from a different formula, right? So don't get fooled by that sucker. Whenever you see that, this might be a decent thing to put in your cheat sheet. Whenever you see something that's got a unit of newtons per kilogram, that's actually an acceleration. So they've told you in a roundabout way that the acceleration due to gravity on this asteroid is 0.25, right? On Earth, it's 9.8. So they said, calculate the radius of the asteroid. You just solve this question for R, all right? So once you know that much, and once you've not been bamboozled by that unit, it's a pretty easy question. Okay. Second, this is 3b. The distance between the center of this asteroid and the center of another one that only weighs 700 grams, this is a tiny asteroid, is 2.6 by 10 to the 4 kilometers. What's the magnitude of the gravitational force that the first asteroid exerts on the second? All right, so this is where you get to this formula. We now have two masses, right, and they're interacting with each other, so we're going to have to use this. But this has a couple of other tricks, this question. 3b. Firstly, one of the masses was given as 700 grams. That has to be put in kilograms, so it's got to be 0.7. Secondly, they gave you the distance between them in kilometers. 2.6 by 10 to the 4 kilometers. That's 2.6 by 10 to the 7 meters. Every distance in physics is in meters. Every mass is in kilograms. Every time is in seconds, no matter how it is delivered to you the first time. They only work in meters, kilograms, seconds. Otherwise, every physics formula will give you the wrong answer. So you had to convert those and then throw everything into this original formula. Excuse me. You're finding the force, you know G, you've been given both of the masses, you've just calculated the R. Okay. So that's reasonably easy. You've got the answer sheet from me, so I'm not going to waste your time telling you what the answers are. I'm assuming you have the question sheet with you. I'm assuming you have the answer sheet with you as well as you watch this video. All right. Question 4, still playing around with space objects, planets. A planet with a mass of 3.12 by 10 to the 23 kilos is in a circular orbit around a star. The planet has a centripetal acceleration of 0.551 meters per second squared towards the star. What is the magnitude of the force? Okay, F equals ma. Right. Again, there are longer ways to do this, but this is always a shortcut that might be available. Okay, so you've been given the mass of the thing, 3.12 by 10 to the 23, hang on, I can't even read this. 23, pardon me, my fault, times 0.551. That's it, F equals ma. What's the magnitude of the force that the star exerts on the planet? That's how it's calculated. It comes to 1.72 by 10 to the 23 newtons. Part B, what is the magnitude of the force the planet exerts on the star? Same answer, right? And that's because of this formula that we just played with before, G m1 m2 on r squared. Gravity is a mutual force between two things. When I jump off a table onto the ground, the reason I end up landing on the ground is because the Earth is forcing me with a certain amount of force. But I'm forcing the Earth towards me with the same amount of force. Because the Earth is way heavier than me, the Earth doesn't move much, and I do all the moving. But we're both being forced by the same force. That is mutual, right? That is the force of m1 on m2, and it's the force of m2 on m1, right? So the answer to A and the answer to B in question 4, the same. Part C, this is 4C. Excuse me. The orbit of the planet has a radius of that. Yep. What is the period of the orbit of the planet in Earth days? So a couple of painful things to deal with here, right? Firstly, it says days, and you know the answers are going to come in seconds. All right. The formula you need to use here is, it's on the data sheet here. You might want to stick it in your cheat sheet as well, or at least give yourself a, pi squared r, pardon me, not pi r squared, divided by t squared. Okay, so the acceleration of one object going around another is 4 pi squared r. That's basically the square of the circumference of the circle it's going around, divided by the square of the time it takes to go around once, the period of it. Excuse me. So you've got that formula on the formula sheet that they give you. You might want to put it on your cheat sheet and just have a little note about when it's used. This is a classic case where it's used. All right. So you're trying to find the period. So you need to solve that, right? So you need to juggle this one around. You're going to get an answer in seconds, right? You've got the R, you've got 4 pi. That's a constant. You've got the A. All right. The answer is going to come out in seconds, and then you have to convert that to days. All right. So the answer in seconds, I'll just look at the answer here. It's 2.327. 2.327 by 10 to the 6 seconds. Right. Divide that by 60 and you've got how many minutes. Divided by 60, you've got how many hours. Divide that by 24 and you've got how many days. So you have to do all of that to this, and you end up getting 27 days. All right. Okay, 4D, the way that the TSSM marking scheme answers this is pretty good. There are a lot of different ways to do this one. It's a ratio question, and a lot of people get scared of ratio questions. I'm going to show you my way to do this. I don't know whether my way is different. A couple of other teachers have sort of raised their eyebrows at my way of doing this, but I think it's pretty easy. So this is how I would do this one. It says a star exerts a force Fy and a force Fz on two other planets, Y and Z respectively. Okay, so I'm just going to go Y and Z and just get a table of information here as I go. All right. And by the way, you can do this in the answer, right? You can put this there. It's absolutely fine. You don't, just because there's lines there, that doesn't mean you have to write stuff on lines. You can just ignore the lines and draw a table or a graph or whatever the hell you want, right? As long as it communicates the answer, you'll get the marks. We don't care how, as long as we understand what you've done. So headings are great, right? Okay, right, so Z has a mass that's 20 times that of Y. Okay, so Y's mass is going to be 1 and Z's mass is going to be 20. It's actually good news when they don't give you the actual figures. You can just make them up, right? So make them simple. That's the easiest way to make that 20 times that, all right? And Y orbits the star. Sorry. Z has a mass that's 20 times that of Y, and it orbits the star at a radius that's 12 times that of the radius of Y. Okay, so R for Y is 1 and R for Z is 12. All right. And it says, what's the ratio of the force due on Y to the force on Z? So I've got to find that. This is my way to do it. Right. So you've got my way and you've got TSSM's way. Here it is for what it's worth. The force is going to be Gm1m2 on R squared. Right. Everything that doesn't change, I'm just going to call it 1. So G is 1. The mass of Y is 1. The mass of the star is 1. The R is 1 squared. So believe it or not, that comes to 1. Right? This just keeps everything as easy as possible. By comparison, same here, m1, m2 on R squared. G is still 1. The mass is 20 this time. Star's mass is the same, divided by 12 squared. Now I've done the mass before. This comes to 1 divided by 7.2. All right, so they are the two numbers that go in here. So that equals, this is Y, 1 divided by 1 on 7.2. In other words, 1 times 7.2, which is 7.2. That's the ratio, okay? So if you're just comparing, it doesn't matter what the formula is, but if you just get a question like this where it says compare, the ratio of this to that, and there are two different things that are guided by the same formula, you can always do this particular way. I think this is the easiest way to do it because it keeps the numbers really simple. And you don't have to be playing around with, oh, its real mass is 2.7 by 10 to the 20 kilograms or something. You don't have to grab a calculator for this. It's a lot faster. All right. Okay, question 5. I'm just going to show you this one on the sheet. It's got a diagram that I don't think was worth me drawing it again. This is better than I'll ever draw. Diagram on the left-hand side of figure 3 shows a wire carrying a current of 1.8 amps being held within a magnetic field. The wire experiences a force of 0.18 newtons. Okay. Find the direction of the force and the length of the wire that's within the magnetic field. Okay, it just says current. So you've got to assume positive current, right? So this is not electron flow. Electrons are going that way. Current, conventional current, the positives that don't really move, are going that way. So right hand, right? Fingers down, thumb here. I'm getting my palm going that way, okay? So it's up the page. That is not out of the page. That is actually up. I know that my finger is actually horizontal now because I'm actually on a table, and yours will be as well when you do an exam, but that direction is up, right? This direction towards the camera is officially called out of the page, and that direction through the table is into the page. That's not up and that's not down. That's up and that's down according to the VCE physics exams, all right? So be particularly careful about ambiguity about the use of the word up and down. Right? Sounds ridiculous, but it does make a difference. All right, so the direction that this one is going to be forced in is up, or you can say up the page. You can even do, or some people do this. Some people actually do this: north, south, east, west, right? And they write north, and then they point to that, and that's fine. That'll get you full marks, right? Again, however you communicate this is fine, but it's got to be clear. And if you just say, and if you say up to something where the answer is actually this way, and you don't say out of the page, you say up, they will mark it as if you mean that way, right? So it's particularly important to call out of the page, out of the damn page. All right, end of harping on that. You also needed to find the length of the wire. All right, so the relevant formula is F equals BIL. And again, this is fairly straightforward. You've got B, you've got I, you've got F in the question, 0.18 newtons. You're just solving for L. And it comes to 40 centimeters, comes to 0.4 meters. All right, pretty straightforward. That's a very easy 3 marks. 1 for that direction, 2 for doing the calculation. That's a bit of a gimme. Now part B says in the diagram on the right side, the wire remains in the same place and carries the same current, but the magnetic field is turned so that its direction is from left to right. All right. Explain why there will not be any force on the wire. So you don't have to tell them, sorry guys, you don't have to tell them that there won't be any force on the wire. So please don't waste your time by saying, there will be no force on the wire in this circumstance because, right? Don't say that. Just go straight, start with the word because, get on with it, right? Just tell them what they don't know. They told you that there won't be any force. So here's why. Excuse me. For there to be a force on the wire, the charge moving through the wire has to be crossing the magnetic field lines at some stage. And because these magnetic field lines are parallel with the wire, that's not happening. All right, question 6, just got to zoom this thing out a little bit. There you go. Question 6, we're going to play around with this a fair bit. This is not the easiest question in the world. Okay, it says, figure 4, which I've reproduced here, shows a coil made of 20 turns, they've only drawn 1, that can be rotated around the axis XY. There was an X and a Y there, right? Forget, they're not talking about that X. Right, so it can be rotated like this. Excuse me. Magnetic field is between the poles. It has a magnitude of 0.73 Teslas. In the position shown, the magnetic flux through the coil is 0.18 weathers. Now, magnetic flux, here's the formula for flux again. It's strength of the magnetic field times the area of the shape that it's going through. All right, that's important. We're going to use this in a second. Okay. A and B are at the ends of the coil. Right. What is the radius of the coil? Okay. In this particular case, the area is a circle, so it's B times pi r squared. So you're just solving this one, right? They gave you the flux, they gave you the B, you know pi, you got to find r, right? Fairly simple. Again, watch the units. I think they all gave you the right units here. Yeah, they did. Okay. Excuse me. And by the way, the 20 turns doesn't come into this yet, right? The amount of flux is just literally how many magnetic field lines are going through the thing. That's pretty much all it is. It doesn't matter how many turns are in the thing just yet. We're going to use the turns in a minute. Part B, the loop produces an average of 72 volts when rotated through a quarter of a turn. All right. What is the frequency of rotation of the coil? All right. So this takes a little bit of unpacking. So the formula you need to use, and again, this one's on the formula list. I'm just going to raise that a little bit. Excuse me. There you go. A little bit more central. Okay. It's EMF, and this is sort of this weird little E for EMF. Right? It's the number of turns times the rate of change of flux. So it's delta flux divided by delta time. All right. So this is what we're sorting out. Now the question said, what is the frequency of rotation of the coil? So we need to find pretty much that. All right. So that's 72. That's 20. Now, in a quarter of the turn, going from where I've drawn it in blue to where I've drawn it sort of dashed in green there, from there to there, the amount of flux goes from its maximum, what it is now, to 0, because when the circle is horizontal, not a single line of magnetic field is going to go through it. It's parallel to it. It's the plane of the circle is such that the lines are parallel to the plane of the circle, so they won't be going through it. So in the time that it takes for 1/4 of a turn, delta flux is all of it, right? It goes from 0.18 Webers, which is what they gave you in the question, to nothing. So that's going to be 0.18. And whatever that time is, that's the time for 1/4 of a turn. So you're going to solve this to find delta T, excuse me, and it turns out to be 0.05 seconds. Right? So then you have to say, therefore, for one turn, for a whole turn, the time is 4 times 0.05 seconds, which is 0.2 seconds. So that's how long it takes to go around once. The question says, what's the frequency of rotation of the coil? Frequency is how many cycles something does in 1 second. It's how many, in this case, it's how many turns something does in 1 second. For a wave, it's how many crests of the wave go past you in 1 second, right? And it's in hertz. So if one of these circles happens in 0.2 seconds, then 5 of them are going to happen in 1 second, right? Or you could just use a formula where frequency equals 1 over the period of something. The period is how long something takes to do something once, right? So it's 1 divided by 0.2, which is 5. Answer is 5 hertz. Okay, we're going to have a go at 6C here. And 6C, this is going to take a while because the answer to 6C is actually incorrect. The explanation is correct, but the actual answer they gave you was wrong. The answer is negative, not positive. So let me just walk you through this whole thing. This is going to be a little bit of a faff. This is about Lenz's law. And we haven't done this for a while, so let me remind you of it. I've got 2 pictures of the same situation. Basically, this picture is you looking at this picture that way, right? From your head being on the side, right? So we'll worry about this one first. Let's have a look at this, right? That is a wire that is going into and out of the page, right? And that's not the head of an arrow. I know we've drawn these things with like a dot there to show that the head of an arrow to show that your current is moving this way. This is a wire that doesn't have any current in it at the moment. All right. So I've just drawn a charge that's in the wire sitting there still. There it is again over here. Right. So that's the same guy. If we move this wire bodily down, right, if we start moving it down, which happens when you spin a loop inside a magnetic field, like 6C is having us do, like this question is having us do. If you move it down there, then that charge suddenly feels an electromotive force on it, pardon me. I'm going to use right hand, and I'm going to use conventional current right-handedness, okay, because this question is conventional current. All right, so to figure out which way this thing's going to go, this charge is going to go, whether it's going to be traveling along this wire out of the page or into the page, use the right-hand rule. Fingers this way. It's being forced that way. So the initial movement of a charged particle is down because the whole wire is being moved down, so every charged particle inside it goes that way, right? Inside a magnetic field that goes that way, and so instantly they will all be forced into the page. So a current is going to go that way. All right. Now, looking at the whole thing from the side, that current ends up going this way, right? If I just turn my hand, right, same thing, right hand, we're moving this thing down. So I've got to put my thumb down, and this time I've got to put my fingers there because we've turned this whole picture that way. So look at this, right? And now my palm is going this way. So we'll induce a current. We will get a current of these things going this way. There are positive charges now moving through the wire in this direction. Now, Lenz's law says that any induced current is going to create its own magnetic field that opposes the original motion that caused the current. That's what Lenz's law basically says. Different books use different phrasing to say that, but that's what they're saying. They're saying that this current that we've created with that movement is going to make its own magnetic force that opposes that movement. I'm going to show you how. There is another right-hand rule, the right-hand screw rule. Remember this one? If there is a current, and again, right hand for positive current, if a current is moving that way down a wire, it creates its own magnetic field that wraps around the wire in the direction that your fingers curl around if you're making a fist. Okay, so the induced current, the induced magnetic field that this current makes goes like this. I'll draw it in blue. My fingers are coming out of the page above the wire and they're going into the page below the wire. So into the page below the wire, out of the page above the wire. So there's now two magnetic fields here. Now if I draw that over here, right, because I've got to poke my thumb into the page this way, right? So there's the current, right? And I actually have to turn the whole thing like that. That's not easy to do without getting out of my chair. But from this vantage point, the current is going into the page, right? So again, if we just do this again, thumb, fingers, palm into the page. So now I have to put my thumb into the page and the current, and sorry, the induced magnetic field is going around this way. So how does that oppose this original motion? Right? It opposes it because this is like a magnet. This gold line is like a magnet with a north there and a south there. Sorry, other way around, pardon me, north, south. Okay. Sorry, I got it right the first time, I'm an idiot. North, south. All right. This one here, this little tiny one there, is the same deal, north to south, right? Tail of the arrow to head of the arrow, right? And this one is one with a south there and a north there, right? So within this big magnetic field that was made in gold with the giant north pole there and a giant south pole there made by the whole big magnet that the loop is in, right? There is now this other little bunch of magnets. And down here, that is a north-south against a north-south. This is two lines of magnetic field that should be opposing each other. If you had two magnets that were both north there and south there, they would repel each other. Right? And over here, this gold line is like a north and a south. This is part of this big thing. And these two magnets here are attracted to each other, right? Opposites attract, right? Like repels, opposites attract. So ahead of this wire, you've got this repulsion pushing it back. And behind it, you've got attraction pulling it back. And so as long as this thing is moving down, right, as long as this thing is moving down, it's actually being pushed and pulled up again by the magnetic field that it creates because of that movement. And that's what Lenz's law is trying to explain. It says any induced current, excuse me, in a wire that's moving in a magnetic field will create its own magnetic field that opposes the original movement. That's Lenz's law. All right, having done all that, I'm going to show you, we're going to finally get back to the question. So this is question 6C, and it says, as viewed from X, and their X is down here, I've mistakenly happened to use an X here, right? When viewed from X, back here. So in other words, when looking at it from where we're looking at it from, the coil is rotated clockwise from its original position shown in figure 4. During the first half of its rotation, from when my X goes from up there to down here, what is the polarity of A? Explain your answer. Excuse me. And it says explain your answer using Lenz's law. All right, here's how you do it. I'm going to answer it in my words first, and then I'm going to show you why the wording of the question, of the answer that TSSM gave you is incorrect. Okay, so my wording goes like this. In order for a force to be going down, using the right-hand rule, the positive current needs to be going in at A and coming out at B. All right, that's the actual reason that it's going clockwise, and it's sucking the charge in at A and pushing it out at B. Right. Now, it said using Lenz's law. So the way to put Lenz's law into that explanation, excuse me, is to say that because it's going clockwise, they said that it was rotated clockwise. Because it's going clockwise, it has to generate a magnetic field that's going to oppose that motion. And to do that using the right-hand rule, the way I did with that other diagram, to do that using the right-hand rule, the movement of the charge the force on the charges in the loop at point X have to be going into the page. And for them to be going into the page, from A, they need to be going into the page. Now, the problem with their answer goes like this. Their explanation is exactly right, but the word positive is wrong. Right? Everything they said is fine. Excuse me. They used some dodgy language, but everything they've said is absolutely fine. But they said, therefore, A has to be positive. Right? And for A to be positive, or if A is positive, that means plus charges are coming out of A, and plus charges are going into B and out of A. To call that positive, that means it's the source of positive charge. And of course, we just right-hand ruled this to within an inch of its life before, and we found out that A has to be going in. All right. If I move that wire down, in a field like that, they're going to be forced into the page. And if these guys are being forced into the page, they're going to take all of these other guys with them. So the plus charges are going in there. And that makes that one the negative, because it means the plus charges are coming out of the other one. Right? Their reasoning was right. I think it's actually a typo, or it might be a copied and pasted version from from the previous year's answer book or something like that. But if you just change the two words positive to negative, it's exactly right. Their explanation is true. Their answer is actually false. Okay, on to part D. We've done enough on 6C. Part D, what is the orientation of the coil when the maximum EMF is produced between A and B? Well, EMF, excuse me, is proportional to the rate of change of flux. Okay, and the maximum rate of change of flux happens when this thing is horizontal, because that's when the movement of these things is at right angles to the magnetic field, and that's when the area of magnetic field going through the circle is changing the fastest. This isn't how big the area is, this is how quickly the size of it is changing. Right? When that circle goes from there to there, there's a big change of area. Right? When the blue circle goes from there to there, right, the change in the area that the magnetic field lines are going through is nowhere near as big. Right? And so the rate of change is nowhere near as big. The rate of change is highest at that horizontal point. All right. And part E is all about slip ring commutators versus split ring commutators. They just call the split ring a commutator in this one. It says the ends of a coil A and B could be connected to slip rings or a commutator in order to draw off the EMF from the coil. What difference does that make, basically? Excuse me. You can draw, and again, by the way, just because they've got lines there, that doesn't mean you can't do a drawing. Right? You can actually answer this using a graph. Let me show you. Instead of trying to write an explanation of this, I think it's probably faster to draw one. So I would go slip ring, split ring, and draw the signal that you're going to get. As long as you label the axes, this will have meaning. If you don't label the axes, they won't mark it at all. Slip rings are just going to give you AC power. Right? Split rings are going to do this to it. They're not going to flatten it, but they're going to stop it from alternating its direction. So split ring, to finish this off, you're going to have to go voltage or EMF and just go time there. Voltage, time. And if you want to write it instead, you can either read what the answers say from the TSSM thing, or I would say slip rings maintain the alternating current that is coming out of the loop, because every loop makes alternating current. Split rings, split rings rectify the alternating current. The word for changing the two directions into one direction is rectifying. Right? So if you want one word to describe what this has done, it's rectified it. Right? So a split ring commutator rectifies an AC signal and makes it direct current, or a variable direct current. Okay? But I would just draw the graphs. Picture tells 1,000 words. Question 7. 3 to go and you've finished this video. Okay. A generator produces electrical power at an average rate of 2.88 megawatts, that's million watts, with a peak-to-peak AC voltage of 6788 volts. Show that the RMS current produced by the generator is 1200 amps. Okay, I'll just a reminder of a few things. Firstly, peak-to-peak versus RMS and all that sort of stuff. Okay, I just drew this graph before. This is the AC signal that comes out of a generator. The voltage can be measured in 3 ways. That distance there is the peak voltage. It's equal to that distance down there. Right. If you add the two together, that is the peak to peak voltage. So all of that is peak to peak. Now, because this is a varying amount of electricity that's coming out of this generator, right? There are times when the voltage is that big, and there are times when it's not. There are times when it's less, and zero there, and then more and more and more. It's varying. The peak voltage, if that's say 40 volts there and that's minus 40 there, the peak-to-peak value is 80, and the peak voltage is 40. But that's a little meaningless, because for most of the time you're not getting anything like 40, you're getting less. You're down here, you're getting like 5, right? So a more meaningful measurement is what's called the RMS voltage. And they basically square all of these numbers, and that just turns these negatives into a positive, because a negative number squared is a positive. They square every last one of these values, excuse me, and then they take the mean of those numbers, right, and then square root it to sort of undo the squaring job. And you end up getting an amount which is about there. Right? So at any one time, the root mean squared, the RMS voltage, excuse me, is quite constant. All right. And of course, there's a formula relating the peak to the RMS, and the RMS voltage and the RMS current, the RMS anything, equals peak divided by the square root of 2. Or it's peak to peak divided by 2 times the square root of 2, because of course you'd have to divide it by 2 and then divide it by the square root of 2. Right, so that's the relationship between the 3 things. All right, so let's get back to this question here, because there is yet another trick in this one. All right, let's do this. 7A. Peak-to-peak AC voltage of 6788. 6788 volts peak to peak. Show that the RMS current, not voltage, they're not talking about voltage in the question. Show that the RMS current produced by the generator is 1200 amps. Okay, so let's get the RMS voltage first, right? RMS voltage equals 6788 divided by 2 root 2. And I'm going to cheat. I've got the answers right with me. Hang on a second. And that comes to 2,400 volts. All right. So RMS current is related to RMS voltage. Now that we've got the right sort of units, we've converted it to the same language, we can now get the RMS current. And you get that by using P equals VI. All right. And the power, they gave it to you in the question, is 2.88 megawatts. So I equals P divided by V, which is 2.88 mega is millions, so it's 10 to the 6th, divided by 2,400. And that comes to 1,200 amps. I would imagine that quite a few people just did that and stopped because they didn't read the word current. They just, oh, I know how to do this, I know this formula, bang, right? And they literally didn't read that you started with voltage and were asked about current. So there's 2 steps in that. That's a fair bit of work for 2 marks. And part B is tricky as well. This is a harder question than it looks. This is one of those questions that looks a bit automatic pilot to a lot of people, to people who have studied well. But if you go too fast, you're not going to see the tricks. So the question says, this is 7B. A transformer with 60 turns on the primary side is used to step down the current to 240 amps. Again, it's talking about the current. So it's not a step down transformer. It's actually a step up transformer because transformers are named after what they do to the voltage. So if current goes down, the voltage goes up. So this is a step up transformer. So, you know, transformers are basically a square block of metal. This one has got 60 turns on the primary side. So the electricity is coming from here and is going out there. And it'll have more turns on the secondary side because it's a step up transformer, right? So it's going to have greater than 60. All right, that's the first little challenge. They even use the phrase step down to try and trick you. It is a step up transformer. All right, how many turns are on the secondary side of the transformer? Excuse me. Let's have a look. You can either use a formula for this, and the answer given in the TSSM solutions just shows you the formula used. So if you want to do that, just have a look at that one, right? I'm not going to show you that one. I'm going to show you my way, which is basically to recognize that the current has gone from 1200, because we just worked that out, down to 240. And that is 1/5 of that. So it's gone down by a factor of 5. And that means that the voltage is going to go up by a factor of 5, which means the number of turns is going to go up by a factor of 5. Okay? And the way to sort of communicate that in the answer would be to do this, right? You go 1200 divided by 240 equals 5. Therefore, the turns will increase by a factor of 5. Right. 5 times 60 is 300. Answer is 300 turns. That's how I would choose to answer it. That's just me though. The other way is to just go to the right formula. You've got the formula in your solutions there. So have a look at that if you don't like the way I did it. Okay, 7C, the engineers want to keep the power losses in the transmission wires to a maximum of 6% of the power produced by the generator. All right, straight away my mind tells me that I'm going to be using this. Power equals I squared R, right? This, VI, that is power supplied. This is power lost, specifically lost in transmitting something down wires, okay? This is power this is how much power gets turned into another form of energy. All right. So we're using this one here. Pardon me. Right, let's see what we have to find. They want to keep this loss, this power loss, to a maximum of 6% of the power produced by the generator. Well, we know how much power was produced by the generator. It was 2.88 megawatts. So first thing we're going to do is find out what 6% of 2.88 megawatts is. So we're going to figure that out. And that is the P. Okay. Now, which I do we have? Because we're being asked for the resistance. So I'll calculate the maximum total resistance of the transmission wires, which will allow this system to only lose 6% and not any more. All right. So the 6% of that, that's the P. What's the I? Now, the I is the I that is the current of the transmission. It's basically, is it the excuse me, is it the 1200 amps or is it the 240 amps? It's actually the 240, right? Because they said in the previous section, a transformer with 60 turns on the primary side is used to step down the current to 240 amps before transmission of the power to a town some miles away. All right. So that new current of 240 amps is the current that it's being transmitted along these wires for. So the I is 240. And you just basically use the I of 240 and 6% of this to calculate what the R comes to. It comes to 3 ohms. Question 8, brought to you by Albert Einstein. We've done these reasonably recently, so I'd imagine most of you are pretty good at this already, so we're going to go fairly fast through this, I think. Question 8a, what's the Lorentz factor for a speed of 0.76 C? Well, again, this is very easy. This is why it's only worth 1 mark, right? The Lorentz factor is 1 divided by the square root of 1 minus V squared over C squared. The V is 0.76 in this case, and the C is 1. Figure it out. The answer is 1.54. Right? So that's pretty straightforward. That's basically, can you drive a calculator? Right? It's only worth 1 mark. And by the way, the Lorentz factor does not have a unit. And that's why the box that they gave you for this question doesn't have a unit in it. Okay. Second question, a spaceship is traveling at a speed where the Lorentz factor is 2.5 and passes a stationary observer who measures the spaceship as having a length of 140 meters. What is the length of the spaceship when it's at rest? It is going to be longer than 140 meters, right? So the two things to remember is what gets bigger and what gets smaller, right? And we've spoken about length contraction. And time dilation. They are the two changes. There is no such thing as length dilation. There is no such thing as time contraction. It doesn't happen. Excuse me. So, if we are in one frame of reference and the spaceship is in another frame of reference, which it is, because it's traveling at a fast velocity relative to us, then we will see the spaceship as contracted, as shorter than it really is. When it stops and gets back into our frame of reference, when it and us are both moving at nothing, it's going to look a lot longer. All right. So the question is really, do you multiply the 140 meters by the 2.5, by the Lorentz factor, or do you divide it by the Lorentz factor? It's going to be one or the other. Right? And again, this is a case where you can either apply the formula. If you're more comfortable just grabbing the formula, then fine, grab the formula, right? But I think this makes a lot more common sense to not even look at the formula. I just remind myself of this, right? If the length is weird, if it's in another frame of reference, it will be contracted, and to find out what the real length is, I have to make it bigger, so I'm multiplying it by 2.5. So the answer to the question is 140 meters times 2.5, and that, I think it was 350 meters. Okay? It is contracted because it's moving. It will stop being contracted and go back to its full length when it stops. All right, so a second, time gets dilated, right? The length of a second when something is moving gets longer, which is why a clock looks like it's going slower on a moving object, right? The passing of 1 second looks like it takes longer to happen. That's dilating time. It's making it go slower, right? Excuse me. Right. So that's part A. Pardon me, that's part B. Part C. What is the rest mass of the spaceship if its kinetic energy is 6.75 by 10 to the 24 joules? Okay, it's moving at a relativistic speed, so you have to use relativistic kinetic energy. Excuse me. And the formula for that, EK equals, pardon me, Lorentz factor minus 1, whoops, times MC squared. They gave you the Lorentz factor. You know what C is. This time you have to put the number in. You can't just put 1 in like this. You've actually got to put 3 by 10 to the 8. Okay? So they gave you the kinetic energy, 6.75 by 10 to the 24 equals, Lorentz factor was 2.5. 2.5 minus 1 is 1.5 times m times 3 by 10 to the 8 squared. Solve that for m. Pretty straightforward. Okay, that is it for question 8, I think. Question 9 is a doozy. And here it is. All right, I've recreated this so I can scroll all over it. I'm just going to zoom this in a little bit. I think we can, there you go, hang on. Yep. Don't get seasick. Okay. Let's take this one step at a time. A spring is placed vertically on a hard surface. When it's got nothing on it, it looks that long, right? It's a great big long spring. It can hold itself up, and that's how big it is when it just holds itself up, right? The spring is compressed 50 centimeters, and then they put a mass on it. Right? So somebody pushed it down and then stuck a block on top of it and let go. Okay. The spring is then released, and the spring extends back to its original length before the metal block comes to rest momentarily. So they've used just the right mass so that when they let go of it, it didn't go like this. It didn't go like that. And it didn't go like this. It went exactly back up to where the spring would normally rest, coincidentally. They picked exactly the right mass. Right? So it's just gone boing up like that, and that's the point where it stops, and then it's probably sort of done a bit of this and has settled somewhere in the middle. Right? But that first release, it coincidentally went straight back up to there and then stopped momentarily before coming back down. So that's what it's telling us. The change in gravitational potential energy of the block between there and there was 24.5 joules. All right. What is the mass of the block? Okay, so we're going to assume that at this point, gravitational potential energy is 0. That's the lowest point it goes, so we're going to call that 0, right? So mgh, which is the formula for gravitational potential energy, equals 0 there, and up here, mgh equals 24.5. So that's the change in energy. What is the mass of the steel block? The mass of the steel block is the m, baby. All right, g is 9.8, h is half a meter, right? They said 50 centimeters. Watch your units. Always be wary of the units. Right, so it's 0.5 meters. We've just got to solve that for m. Okay, so m times 9.8 times 0.5 equals 24.5. Therefore, m equals, I'm going to check out what the answer is. It's 5 kilograms. Okay, 5 kgs. All right, just going to zoom this out a little bit more. You need you to see more page. Okay. So that's part A. Part B, show that the magnitude of the spring constant is 196 newtons per meter. Okay. The way it got that energy is from the spring, right? So down here, given that the only energy that it's got is spring energy, is elastic potential energy, it must have an elastic potential energy of 24.5 joules. This is a conservation of energy question. Up here, when it rose up here, they deliberately told you in the question that it wasn't moving. So that's confirmed that it doesn't have kinetic energy when it's up here. It also doesn't have any more elastic potential energy when it's up there, because we know that this is where the spring would normally rest. Right? So it's got no elastic potential energy when it's just hanging around minding its own business. And that's its hanging around minding its own business length. So the only energy that it's got there is gravitational. So that's the total amount of energy it's got, 24.5. And the only energy that it has down here is elastic potential energy. And so it must be 24.5, because again, now it doesn't have any gravitational potential energy, and it's also not moving. It doesn't have any kinetic energy either. Right? So point A, point B. And again, in your answer, by all means, feel free to draw all over the diagram that they give you and refer to your drawings and your sketching. So you can do this and then say, at point A, this is totally legit answering of physics questions in a VCE exam. It's absolutely fine. Excuse me. They will look for the point A and they'll assume that you've labelled the diagram. If you don't label the diagram, of course, you're writing something meaningless. So do that. So do everything properly. Okay. Show that the magnitude of the spring constant is 196 newtons per meter. Okay. Well, elastic potential energy is a half kx squared, and that's the spring constant, and we know that, and we know that. 24.5 equals a half times k times it has been compressed by half a meter. So it's 0.5 squared. And you just have to solve that for k. Okay. And therefore k equals, and of course they gave it to us in the question, 196 newtons per meter. And that's all you have to do. Right? You don't really have to show them the calculations. You don't have to show them this rejigged, right? Once you've put the right numbers in the right spot, in the right formula, the person marking the exam knows that you've gone from there to there, right? Okay, so that's how to do B. Just let me pause this for a minute. Okay, sorry, just dropped something. Part C, last one before we end this video. The acceleration of the block is 0 at the point halfway between the lowest and highest points. I've done that here. Right? Lowest point is there. Highest point is there. That's halfway. So this is point C. This is where question C is at. Okay. The acceleration of the block is 0 there. That means it's traveling at its fastest there, right? Because if you analyze this properly, it's not moving at all there. It's also not moving at all there. This is where it stops going down and starts going up. This is where it stops going up and starts going down, right? So at those two extremes, it ain't moving, right? As it moves up from here, the spring is accelerating it, speeding up, speeding up, speeding up. Right? As this moves down here, gravity, the mgh that it's got, right, is accelerating it down. Right? In the middle, that is where the maximum velocity happens, on the way up and on the way down. Right? So we're looking at this question here. And the question says, show that the maximum kinetic energy of the block is 25% of the total energy of the block, assuming that the gravitational potential energy of the block is 0 at its lowest point, which we have done. All right. So that assumption just tells you that the total amount of energy that this thing has at any point in its trip is 24.5. So at that halfway point, that 24.5 is a combination of all three. It has some gravitational potential energy because it's got an H. It's got an M and a G and an H there. The H is 0.25 meters because it's halfway up that trip. Right? So H equals 0.25 meters there. Right? It also has elastic potential energy because we know that it rests that long and it's still a little bit compressed, which is why it's still sort of pushing this thing up. Right? But gravity's starting to take over. All right. So we also know that the compression, the X of the spring, is that 25 centimeters, 0.25 meters. So we know that that's the X at this instant in time. And we also know that at any point, the total energy equals the kinetic energy plus the elastic energy plus the gravitational energy, right? And we're going to use that and these to figure out that. So that's what we're going to do. So fleshing out the whole thing, I'm just going to go down a little bit. total amount of energy. I'm just going to put the whole thing down here. Sorry about the line. Total amount of energy is 24.5 joules. That equals its kinetic energy, which is what we're trying to find. So we're just going to leave that. Plus the elastic potential energy, which is a half kx squared. K, we found out before, was 196. X squared, 0.25 squared. That's that bit. Plus gravitational potential energy, mgh. We know it's 5 kilograms now. mgh, 0.25. And we're solving that for kinetic energy. And when you solve that for kinetic energy, it's going to come to be a quarter of that. That's what the question said. Right? It said show that the maximum kinetic energy, that is its maximum because that's where the V is biggest, sorry. Show that the maximum kinetic energy is 25% of the total energy. And when, trust me, I'm not going to do this in front of you, that'll be a waste of your time, but trust me, when you get the answer, excuse me, it comes out to 6.125, which is indeed a quarter of the total. All right, that is the end of this particular video. I'm going to answer questions 10 to 17, the last lot in video number 3, and that'll be it for the TSSM exam from 2019. Thanks.